The last of the catalyst videos I'm going to do is on page 25 of the booklet, and it involves the reaction of ethanedioate with manganate ions. Now, ethanedioate, our most common source of that is from iron 2 ethanedioate, which is FeC2O4. And manganate, very important chemical, especially in redox titrations. We get that from potassium manganate 7. Make sure you can see all that. Yeah, so potassium manganate 7, which is KMnO4. The potassium in this isn't important, the potassium ion. It's the MnO4 minus ion that we're dealing with here. Now, the iron in iron 2 ethanedioate, that can undergo a chemical reaction, but I'm not concerned with looking at that at the moment. The Fe2 plus can be converted into Fe3 plus. All we're going to look at in this catalysis reaction is for the reaction of the C2O42 minus ion with MnO42 minus. Now, this is the only example that you need to know of an autocatalyst. Now, an autocatalyst is defined as it's a species that catalyzes a reaction or catalyzes the reaction from which it was formed. So it gets produced and then it goes back and actually reacts with the reactant in one way or another and speeds up that reaction. Now, before we even get onto that anyway, we need to look at how these two species react with one another. You may need to form an overall equation. Now, the thing that you need to remember about this is whenever we're dealing with MnO4 minus, it almost always turns into Mn2 plus. Now we need to write a half equation for that. So manganese balances 4 oxygens, we need 4 waters, we need 8 H pluses on this side, and then on the left it's +7, on the right it's +2, so we need 5 electrons. C2O42 minus, that gets converted into CO2. So we need to balance the carbon, 2 of those. That balances the oxygen, so we've no need for water or H+, but we need 2 electrons. Now, when we're going to combine both of these, electrons don't balance, so we'll multiply this one by 2, this one by 5. So we'd have 2 MnO4 minus plus 16H plus. I'll leave out the electrons again, plus 5 C2O4 2 minus, and that forms 2 Mn2 plus 8 H2O plus 10 CO2. So that's the overall equation. But after watching the last video, the first homogeneous catalyst video, you should notice we've got 2 negative ions once again reacting with one another. So this will have a slow initial rate, and that's because we've got 2 negative ions repel, and that also means that it will have a high activation energy. We'd need a lot of energy to get those two to collide with one another successfully. Now, the interesting thing with this reaction is we do have a slow initial rate, but the rate actually begins to speed up. And what actually happens is our autocatalyst is Mn2+. That Mn2+ goes back and reacts with MnO4-. So we can't really set this up in the way that we've done all the previous ones, two half equations for the reactant species of that turning into that and that turning into that, and then the Mn2+ and its other counterpart catalyst Mn3+. I suppose we could do, but you really need to understand what goes on in the pathway of the reaction, because this reaction changes as it progresses. So we have that reaction occurring very slowly in the first instance. We start to build up Mn2+. Now Mn2+ reacts with MnO4-. So you can see immediately we've got opposite charges. So these are going to react, and it forms Mn3+. So what we now need to do is we need to do half equation for MnO4- converting into Mn3+, and Mn2+ converting into Mn3+. So all of the manganese gets converted into Mn3+. So this one's easy. We just need one electron on the bottom there. This one, 4 oxygens, 4 waters, 8 hydrogens, 8 H+. This side is +7 at the moment. That is +3, so we need 4 electrons here. Now we're going to combine both of these. 1 electron there, 4 electrons there, so we'll multiply that one by 4, and we have, I'll just sort of reorder it a bit, MnO4- plus 8H+ plus 4 Mn2+ goes on to give, well, I'll just group all these together. That will give us 4 Mn3+ plus that one there, which will be 5 Mn3+. Then plus 4 H2O. Just double check the charges. Plus 15 on that side, and 8 plus 8, 16, minus 1, plus 15. So that is our one equation for how Mn2+ behaves as an autocatalyst. So that starts the autocatalyst or the catalysis process off. But it's not complete. We formed Mn3+. This is our intermediate species that obviously needs to be converted back into Mn2+. And what happens here is the Mn3+ formed in that converts into Mn2+ by reacting with our remaining product, C2O42-, which still goes into CO2. So we've already got that half equation up the top. And this one just needs that. Much simpler equation to combine that and that. So we'll multiply that one by 2. So we'll have 2 Mn3+ plus C2O42- gives us 2 Mn2+ plus 2 CO2. And that's our second one. So these are the two equations which show how Mn2+ behaves as an autocatalyst. It initially gets produced in this equation, and then the Mn2+ goes back, reacts with the MnO4-, and what we can see with this is we actually need to build up quite a large amount of Mn2+, a 4-to-1 ratio. So this won't happen instantaneously right at the start. We need to build up Mn2 plus stocks in the reaction. So it starts off very slowly due to the negative ions repelling. But then once we've got sort of critical mass of Mn2 plus, that starts reacting with that. And then it starts escalating. The Mn3 plus will then go and react with the C2O42 minus, making more Mn2 plus, which can then go back and continue to react with the MnO4 minus. Now, there's one other aspect about this. This practical can be followed in something called a spectrophotometer. So you should have covered the previous pages in the booklet regarding colorimeters or spectrophotometers. Now, the important factor about this is that MnO4 minus is a dark purple solution. It essentially looks like a neat Ribena. So it's a very dark solution, very little light passes through it. You can't see anything through the background of it. But when it gets converted into Mn2 plus, now Mn2 plus does have a hint of a colour, but to all intents and purposes, it's essentially colourless. Remember, anytime you're stating observations, you need the colour and you need the phase in both. And we never ever say clear. It's always colourless. Never write clear down. So if we were monitoring this reaction, and with a spectrophotometer, what you've got is you've got a cuvette. So a cuvette is just it's a small plastic container, and it's about 1 centimetre wide. If you've got your reactants in here, so at the start, you've got MnO4 minus and C2O42 minus. That's going to be a very dark purple. A dark purple solution. So a spectrophotometer works by shining light through, and just like your bottle of neat Ribena, because that's so dark in there, very little light is going to come out and be picked up by the detector. So this, at the start, absorbs a lot of the light. It has a high absorbance. So we abbreviate absorbance to ABS. Now, as that reaction proceeds, after a while, while that reaction's occurring in that cuvette, what's happened is all of that MnO4 minus has now turned into Mn2 plus. And the Mn2 plus is now essentially colourless. The other product, carbon dioxide, would have hopefully bubbled away, and we just have water in there. So all of our light that passes through there will all pass through now. So it will have a low absorbance. Now we can track this over time by monitoring the change in absorbance from that spectrophotometer. And if you were to plot it over time, so we'd have absorbance against time. At the start, where the rate is very slow, that absorbance wouldn't decrease much. It would still be a very dark colour. So if we started up there, high level of absorbance, and the change in the absorbance will be very slow, almost flat. But then, after we've produced a critical amount of Mn2 plus, the autocatalysis process kicks in, and that rate of reaction increases. More of the MnO4 minus gets converted ultimately into Mn2 plus, making that solution a lighter purple, or eventually turning into colourless. And that occurs like this. So we get a very sharp increase in the rate, until a point where we start to run out of the MnO4 minus. So because we're running out of the MnO4 minus, we've got fewer collisions between the Mn2 plus and the MnO4 minus, so the rate starts decreasing as we'd expect with a reaction. So the rate falls, and obviously it becomes more of a colourless solution a lot slower, until eventually the colour stabilises and the reaction's finished. So the distinct zones on this graph that you'd need to explain: 1, slow initial rate, and that's for the reasons explained earlier. I'm running out of space, so I won't write anything else about that. But the two negative ions repelling each other, high activation energy, slow initial rate, slow change in colour, or slow decrease in absorbance. Then, for part 2, Mn2 plus concentration increases. We get autocatalysis occurs, rate increases. And then finally at 3, concentration of MnO4 minus is very low. Therefore we get a slow rate. So there is quite a lot to that particular equation. So you do need to know that, and you do need to be able to regurgitate it. So you need to make sure that you have learned what an autocatalyst is, but also what each of the two reactants turn into, but then what happens to Mn2 plus and how it autocatalyzes, if that's a word, or the way to pronounce it anyway. So that turns into Mn2 plus. Combining the equations, getting the other equation, the one with C2O42 minus, which is a lot simpler, and then also explaining how this practical, or this experiment could be followed using a colorimeter or a spectrophotometer, and also understanding the reasons as to why we can use a spectrophotometer or colorimeter, which is due to the large difference in colours and being able to track the absorbance of light through each of these containers that we're holding the reaction mixture in. All right, if you have any questions with that one, because it is a complicated one, do email myself or Kath. Thanks a lot.